100 years ago, the invention of the transistor, hailed as the greatest invention of the 21st century, laid the foundation for the development of integrated circuits, microprocessors, and computer memory. The three co-inventors of the bipolar junction transistor were awarded the Nobel Prize in Physics in 1956. Hello, everyone. Welcome to the Analog Electronic Technology course. In this video, we will introduce the bipolar junction transistor. In the family of electronic components, the bipolar junction transistor plays a crucial role. It is a semiconductor device capable of current amplification and switching. It can amplify a weak input signal into a stronger output signal. In fact, this amplification is a process of controlling energy conversion. Essentially, it transforms the energy from the power supply into output signal energy. Below are several common physical images of bipolar junction transistors. Bipolar junction transistors are widely used, come in many varieties, and can be classified in various ways. From the internal structure perspective, bipolar junction transistors can be divided into NPN and PNP types. Their basic structures and symbols are shown in the figure. The NPN transistor is on the left and the PNP transistor on the right. Externally, a bipolar junction transistor has three terminals: the base, collector, and emitter. In addition, a bipolar junction transistor contains two PN junctions and three semiconductor regions. The arrow in the symbol indicates the actual direction of the emitter current. Due to the different charge carriers involved in conduction, the current directions in NPN and PNP transistors are opposite. In the future, we can determine the type of a bipolar junction transistor by the direction of the emitter current. Whether it is a NPN or PNP transistor, its structure appears vertically symmetrical, composed of two back-to-back PN junctions. So, can two individual diodes connected this way be used to replace a bipolar junction transistor? The answer is no. Bipolar junction transistors have their unique characteristics. To achieve amplification, internal conditions must be met, namely the internal structural characteristics of the bipolar junction transistor. The emitter region is heavily doped. The base region is the thinnest and has the lowest doping concentration, about 2 to 3 orders of magnitude lower than that of the emitter region. The collector junction has the largest area, and the collector region's doping concentration is lower than that of the emitter region. Furthermore, the amplification function of the bipolar junction transistor is realized through charge carrier transport under certain externally controlled conditions. Thus, for a bipolar junction transistor to achieve amplification, the following external voltage conditions must be met. The emitter junction must be forward biased, and the collector junction must be reverse biased. We will take an NPN transistor as an example to understand its amplification mechanism by examining the movement behavior of charge carriers inside the bipolar junction transistor. As shown in the figure, based on the applied external voltages, we add two DC voltage sources, V and VCC, between the three terminals of the bipolar junction transistor. VE forward biases the emitter junction, while VCC reverse biases the collector junction. Here, you are required to recall the movement behavior of charge carriers inside a PN junction under forward and reverse bias conditions. In the emitter region, which is heavily doped, diffusion dominates under forward bias. Electrons from the emitter diffuse into the base region. forming the main diffusion current IN. The few holes in the lightly doped base region also diffuse into the emitter region, forming a diffusion current IEP. Both currents flow in the same direction. Although IEP is much smaller than IN, all contributions matter. Every bit of power counts. The sum of IN and IEP gives the emitter current IE. Meanwhile, a small portion of the electrons diffusing into the base region recombine with holes in the base, forming the base current IBN. The directions are shown in the diagram. Now, everyone consider this. Under the effect of the reverse bias voltage VCC, where do the charge carriers that have diffused into the base region go? The reverse bias voltage enhances the internal electric field of the depletion region, strongly attracting electrons at the base collector junction boundary, causing them to drift rapidly across the junction. This forms the collector current ICN. Similarly, minority charge carriers, holes, in the collector region also drift, generating a reverse saturation current ICBO. ICBO is not controlled by the emitter voltage VBE and does not contribute to amplification. It depends solely on temperature and the concentration of minority charge carriers. Naturally, the smaller, the better. Based on the previous discussion, we can summarize the movement behavior of charge carriers inside a bipolar junction transistor with the following three statements. Forward bias at the emitter junction causes diffusion, generating the emitter current IE. Electron-hole recombination in the base forms the base current IB. Reverse bias at the collector junction strengthens the internal field, and drift generates the collector current IC. From this, we then derive three current divider rules. First, IE equals IB plus IC, which illustrates the movement of charge carriers across the three bipolar junction transistor regions. Second, IC equals ICN plus ICBO. During the entire charge carrier movement, the two types of charge carriers in the bipolar junction transistor, majority charge carriers and minority charge carriers, both participate in conduction and together form the collector current IC. This equation highlights that the bipolar junction transistor is a bipolar device, i.e., a bipolar junction transistor. Because minority charge carriers also participate in conduction, the bipolar junction transistor's temperature stability is poor and easily affected by temperature. This is a disadvantage of bipolar junction transistors. Moreover, in future engineering estimations, focus on the main factor. Since ICBO is only at the microampere level, it can be neglected compared to ICN, which is in the milliampere range. Among the three terminal currents of the bipolar junction transistor, there is another important equation between IC and IB. Beta equals IC divided by IB. Here, beta is defined as the current amplification factor. It is a parameter that typically ranges from several tens to several hundreds, and it is a number much greater than 1. This shows that the bipolar junction transistor uses a small base current IB to control a much larger collector current IC. The bipolar junction transistor's small controls large mechanism can be compared to a water tank. The drain pipe is controlled by a valve. Slightly adjusting the valve changes the water flow significantly. The water tank is like the collector, the valve is the base, and the drain pipe represents the emitter. When a small bias voltage, around plus 0.7 volts, is applied to the base, the valve opens, allowing water to flow rapidly, i.e., current flows from C to E. If the base bias voltage of the bipolar junction transistor disappears, the valve closes, the water stops flowing and the current from collector to emitter drops to zero. Thus, in the active region of the bipolar junction transistor, by simply controlling the externally applied emitter junction voltage VB, the base current IB will change accordingly, which in turn controls the number of majority charge carriers in the emitter region and ultimately regulates the collector current IC. From the principle of bipolar junction transistor amplification, it is clear that the so-called amplification does not mean directly amplifying the base current IB, but rather using a small IB to control a much larger collector current IC. To the external circuit, it appears as though IB has been amplified. This is akin to leveraging a small force to move a great weight. Hence, the bipolar junction transistor is a device with current amplification capability, where a small current at the base controls a large current at the collector. Everyone, we have just explored the movement behavior of charge carriers inside a NPN transistor and derived 3 important current divider rules, thereby understanding the bipolar junction transistor's amplification and control functions. Now, if we switch to a PNP transistor, what similarities and differences would there be in comparison with the NPN transistor? Please discuss this question among yourselves. Alright, that concludes our introduction to this topic. Thank you all for watching.